So following up on Derek's question, we talked about if you have a stable equilibrium, then the oscillations would be damped. And if you go back to the dashed line represents the equilibrium radius. For a pulsating variable, the oscillations are what we call overstable. We say it's overstable in order to distinguish it from unstable. So in other words, if the star were truly unstable, then what would happen is that it might have some equilibrium radius, but if you, and no actual star behaves this way, but in other words, if you have an unstable situation, then the force is in the same direction as your displacement. So for example, what if I expanded the star, and in that case, pressure was stronger than gravity? Then it would want to keep on expanding, and at least initially you get an exponential growth of the perturbation, so it just takes off. It just grows bigger and bigger and bigger. That would be unstable. Overstable is where I expand the star. Notice I'm starting with it bigger than its equilibrium radius. But there's a restoring force. Gravity is stronger than pressure, so it falls back in. But if what happens is that it overshoots the equilibrium and then sinks further inwards, compresses more than it would have without some input mechanism that provides extra energy, that's when you've got overstability. In other words, if the oscillations grow with time, if it's still oscillating so that there's a restoring force that keeps restoring you to the equilibrium radius momentarily, but if the oscillations amplitude grows with time, we call that overstable, to distinguish it from stable, where they would damp away, and unstable, where there was never a restoring force. There was always a force away from the equilibrium, so that the perturbation just plain grew exponentially with time. So those are fairly common terms when you talk about stability analysis. You distinguish between stable, unstable, and overstable. So, to get some insight into what's going on here, I'm going to zoom out now because I don't need the screen for a while. Let's consider oscillations of a weight in a piston. Have you guys talked about heat engines in StatMech? Did you talk about them in...
We skipped that chapter.
Skip that chapter. Did
We're
you talk...
probably come back to it.
Did you do it in Physics 110 or 111 at all? Talk about heat engines, like Carnot cycles and stuff like that. Okay, well, I'll give you a little bit about that here, basically. There's this neat analogy between a pulsating variable star and a two-stroke gasoline engine. Turns out they're both heat engines.
Yeah, that's chapter 4. I think we'll go back to this. I'm not sure when.
So to gain insight into stellar oscillations, consider the oscillations of a weight in a piston.
Is that inside or
Third hour. Yeah.
We just started too.
guess I should, well, the piston is really the thing that moves in a cylinder. So of a weight in a cylinder, and the weight is going to be part of a piston. That's how I should really think of this. So here's a cylinder, like in a gasoline engine, for example. And so my weight will just be a disk here. And I will attach it to a shaft so that we've got ourselves a piston, basically. And in here is trapped gas. And what we can say is that at equilibrium, the temperature of the trapped gas equals that of the surroundings, because otherwise heat will flow into or out of the trapped gas and change its pressure, and then we won't be in equilibrium. So at equilibrium, the temperature of the trapped gas equals that of the surroundings. And the pressure exceeds that of the surroundings sufficiently so as to support the weight of the piston. So in other words, the pressure of this gas here should be higher than the outside gas pressure because it needs to balance the extra weight of the piston pushing down on it.
Oh, that seems like it's
It does, doesn't it?
It was like one of the first things we done.
Is it really?
Yeah.
Well, good. That should be helpful to you then. And the pressure exceeds that of the surroundings sufficiently so as to support the weight of the piston. And as physicists, we're never ones to let well enough alone. So what we're going to do is we're going to say, I'm going to walk up to this thing, and I'm going to quickly push down on the piston and then let go and ask what happens. So now imagine pushing down quickly on the piston and letting it go so quickly that heat has no time to flow out of the trapped gas. Because when I push it downwards, I'm going to do PV work on that trapped gas. I'm going to heat it up. We want this to happen so quickly that there's just not enough time for that hotter gas to start transferring heat to the surroundings. Okay, so in other words, it's an adiabatic compression is what it comes down to for these purposes. Now imagine pushing down so quickly on the piston. And letting it go, or pushing down quickly on the piston, not so yet. Quickly pushing down quickly on the piston and letting it go. So quickly that heat has no time to flow out of the trapped gas. argue that this piston will oscillate. So the adiabatic pressure will the adiabatic compression will heat the gas because they do PV work, they do PDV work on it. And that means that now the pressure will be more than enough to support the weight of the piston. And so therefore, there will be a net upwards force on the piston. So it's going to start rising. When it gets to equilibrium, it's still moving, so it will overshoot. And then the trap gas will start cooling down as it expands. The pressure will drop so that after it overshoots the equilibrium, there won't be enough pressure to support the weight anymore. It's still moving, but now gravity on the gravity force on the weight exceeds the pressure force on it. So it starts to slow down, stop, reverse, fall, overshoot the equilibrium. So you get a cyclic oscillation again. So this will vibrate, it will oscillate, like we were arguing the star would do. The adiabatic compression heats the gas. The higher density and pressure drive up the pressure. The higher density, density and temperature, I meant to say in my notes here, drive up the pressure. So there's a net upwards force on the piston. It will rise, overshoot the equilibrium, yada, yada, yada. Yada, yada, yada. So the piston will oscillate. It's oscillating because it's on a spring of air, so to speak. You can think of the air trapped inside as acting like a spring. When you compress it, it pushes back harder. When you expand it, it's not pushing back as hard. It's not pushing as hard, which means the outside air is pushing harder, in which case you would feel a suction because it's really the outside air pushing down harder than the inside air. If you're pull this up, it feels like it's sucking on you. It's not that the air is sucking on you literally, it's that the outside pressure is staying constant, but the inside pressure is going down, and so there would be that downwards force on the piston. And to counteract it, you'd have to be pulling up, so it would feel like suction to you. It's not that it's being sucked in, it's that the outside air is pushing down harder than the inside air is pushing up. Anyway, what questions do you have? Okay, so if the cylinder walls were truly insulated, they wouldn't let any heat flow in or out, why then the oscillations would be adiabatic, no heat flow in or out. And in that case, they would not be damped if there were no friction also. There'd be no damping because at any given time, essentially, you could think of the work being done as storing potential energy, if you will, because well, I'll just write it out, but essentially you'd be trading back and forth between gravitational potential energy and thermal energy in the gas, is what it comes down to. The cylinder walls are perfectly insulating. Oscillations will be adiabatic. No heat flow in or out, which also means the what is constant. If there's no heat flow, then the what is constant. It's an E word. I'm just guessing that you've talked about this. The entropy would be constant. It'd be a constant entropy because remember, ds is dq over t. And so if dq, the heat flow is 0, then the entropy change is also 0. The oscillations will be adiabatic. All work done on the trapped gas during downstrokes, when the piston is moving downwards, is stored as internal energy. And I'm saying downstroke because we're going to talk about engines, and engines have what we call strokes, where the piston is moving up or down, basically. So this is going to be a downstroke, or a compression stroke, if you will. All work done on the trapped gas during downstrokes is stored as internal energy. So in the relationship that the change in the, from like the, I guess what's the first law of thermodynamics, the change in the potential, the change in the internal energy of the gas is heat flow in minus work done by dq minus pdv. Since there's no heat flow in, then all the internal energy change is due to the pressure volume work. du is minus pdv in this case. And all work done by the trapped gas during upstrokes, because that's when the pressure of the trapped gas is pushing in the same direction that the piston is moving, so it's sort of positive work on it. All work done by the trapped gas during upstrokes comes from the internal energy. So when the piston is moving down, gravitational energy is being converted into internal energy of the gas, and when the piston is moving up, it's the other way around. Internal energy of the gas is increasing the potential energy, is being used to increase the potential energy of the piston as it rises. And the kinetic energy, that's in there too, but if you look at only when the piston is maximum or minimum height, then that's a case where you just change its potential energy by some certain amount over the entire half cycle. So anyway, what it comes down to is we thus have a spring of air. And we'll get oscillations of constant amplitude amplitude. They won't be sinusoidal because you won't have Hooke's law. It won't be true that the force is proportional to how far the piston moved, but they will be constant amplitude, quasi-sinusoidal oscillations.
I like the word quasi.
What?
I like the word quasi.
Quasi, yeah. It's a good word. You know what the German word for quasi is?
What?
Quasi.
I was really expecting something better. A little disappointed.
Sorry. And we get oscillations of constant amplitude, albeit non-sinusoidal ones. So we can plot this on what's called a PV diagram. You guys done PV diagrams? Okay, so what's that?
I've never heard of such a thing.
You've never heard of such a thing. Said in such a way as to clearly indicate that yes, we've definitely done PV diagrams.
What is a diagram?
What's a diagram? Is that what you said? Well, I can't work with you if your question is what is a diagram?
That's not the spirit.
That would be, you need so much remedial work. I just, you need to take some more courses before you do this one. So in other words, the idea is, in the PV diagram, the trapped air, if you look at its pressure and its volume, it's always a point along that curve, and the arrows indicate that it's just going back and forth between some maximum pressure, minimum volume point, and some vice versa, maximum volume, minimum pressure versus maximum pressure, minimum volume. So then if you guys have done PV diagrams, I presume you've talked about, for example, if I go from some, if I went between some state of low volume, high pressure to, low volume, high pressure to high volume, low pressure, is that the gas expanding or contracting? Would this correspond to expansion or contraction? Would this be the cylinder moving up or the piston moving up or down?
Expansion, so.
Yeah, so this is right, piston moving up. We've got TU is minus PdV, right, because there's no dq here. So what does that area there represent?
The work done.
That's the work done, yeah, right. Area under curve equals PV work done on, since it's expanding, on the surroundings by the trapped gas when the cylinder is moving up. On surroundings by trapped gas as cylinder moves up. Because there it's putting a force in the same direction the cylinder is moving, so it's doing positive work on the surroundings. So it's losing internal energy by this amount. This is the amount of work it does on the surroundings, and that's equal and opposite to the change in the internal energy. So this comes at the expense of its internal energy. It does work on the surroundings at the expense of its own internal energy. What if I trace the curve the other way? What's the interpretation?
Compression.
Yeah, turn it around, right? This would become the area under that curve is the PV work done by the surroundings on the trapped gas, increasing its internal energy. Probably should, I said on the surroundings, I probably should have said, well, it's okay, it doesn't, it's just as long as you're consistent. So work done on gas by surroundings during compression. Gains this much internal energy. So for these adiabatic oscillations we're talking about here, notice what we're saying is that just as much work is done on the gas during the compressions as is done by the gas during the expansions. So that's why the oscillations will not damp down or grow. It's because we're in this equilibrium where in every cycle there's no net work done because just as much work is added to the gas during the compressions as it gives back during the expansions. That's the idea here. And notice it's the retracing of the curve in the PV diagram that indicates that. Adiabatic oscillations the gas does exactly as much PV work on its surroundings during expansions as is done on it by the surroundings during compressions. So now let's consider what happens if the walls are not perfectly insulating, so heat can flow in and out. That, yes,
I like the movement.
yes. That's going to damp these oscillations.
You go down to harmony. We're going to call it the harmony dance move.
That's right, yes. Right, yes. I present an interpretation.
We just call it the harmonic oscillations.
The harmonic, the damped harmonic cylinder oscillations. Bravo, bravo.
Forest theater.
No applause, just throw me cash. Now suppose the cylinder walls are not perfectly insulating. Well, that's going to screw things up, so to speak. At max compression, the trapped gas is at its hottest. As the piston rises, heat thus flows into the surrounding gas. So what that means is the temperature and the pressure are going to be lower than they would have been as it's rising for perfectly insulating walls. The pressure and temperature of the trapped gas will be lower than what they would have been for perfectly insulating walls. And that means by the time it reaches the equilibrium height, it won't be moving as fast as it would have been because the pressure force on it was always less than if no heat had been flowing. So by the time it gets to equilibrium height, it's not moving as fast as it would have been if the walls had trapped all the heat and not let any heat get out. So piston will be moving slower when it gets to the equilibrium height. And that means it's not going to rise as high as it would have been. In other words, the oscillations are getting damped. It doesn't rise. It keeps going past the equilibrium, but not as far as it would have because it's not moving as fast as it would have. So it doesn't rise as far as it would have. The oscillations are dying down in amplitude. go up as high as it would have for perfectly insulated walls. And it works the other direction too. So make the argument for the other direction when it's up at maximum expansion, when it's up at its highest height there. Compare the temperature of the gas inside to the temperature of the gas outside. Trapped gas, is it hotter or colder than the outside gas when it's reached its maximum point of expansion?
It's colder. The trapped gas is colder.
Trapped gas is colder, yeah, because it's cooling off as it expands, right? It's doing work on its surroundings, so that's at the expense of its internal energy. So as it expands, it's cooling. So when it's at maximum expansion, when it's as far up as it gets, the gas trapped inside the cylinder is colder than the surrounding gas. So which way does heat flow?
Back in.
Back in. That heats it up so that it stays warmer on the way down than it would have for perfectly insulating walls. The pressure stays higher, gravity is not as effective at getting it to fall, so it's not moving as fast in equilibrium as it would have been for perfectly insulated walls, so it's not going to fall as far as it would have for perfectly insulated walls. So it works both directions. Heat flow into the gas while it's rising. Heat flow out of the gas while it's rising works against it rising as high as it would have. Heat flow into the gas while it's falling works against it falling as far as it would have. And so every cycle is lower in amplitude than the one before it, and you get damped oscillations because of heat flow in and out of the gas from the surroundings during the oscillations. So, conversely, heat flow into the cooler gas as the piston falls toward equilibrium. Means it also overshoots the equilibrium on the way down, less than it otherwise would. Less than for perfectly insulated walls. Damped oscillations. And of course, good old friction between the weight and the walls of the cylinder will also dampen it. But even if there were no friction, even in the complete absence of friction, you would still find that there was damping because of this heat flow in and out business. ultimately what will be happening is that you did work to push the cylinder down when you started this whole thing. And if there was no heat flow back and forth and no friction, then that energy you imparted stays there as it oscillates up and down. If there's heat flow back and forth, whenever heat flows, entropy increases, right? And so ultimately what happens is the system increases its entropy, meaning that in the end, everything's just warmer than before. The work you did just turns into all the gas is a little warmer than it was before. It just gets thermalized is what it comes down to. What questions do you have? Okay, so now let's consider what happens in an engine. So in particular, there's 4-stroke engines like in an actual automobile, but if you have a lawnmower, it's a 2-stroke engine, and the 2-stroke engine is a better analogy with what happens in a pulsating variable star. The idea is that in our 2-stroke engine, there's a compression stroke and an expansion stroke, if you will. There's a time when in this case, the cylinder is vertical, so the piston moves up and compresses the gas, and then there's times when the piston's moving down and it's expanding the gas trapped behind it. And the key to driving the engine is that when you're at maximum compression, you fire a spark plug and light a fuel-air mixture, and then that ignition of the fuel-air mixture heats the gas while it's at maximum compression, and drives its pressure up. And so, how does that change things? Well, let's look at the PV diagram. So, here we are in the compression stroke. It's happening rapidly, so essentially it's adiabatic. And so you just follow an adiabatic curve on the PV diagram. But then you burn fuel. And if you burn fuel quickly, the piston doesn't have time to change direction or move really during the burning of the fuel. So if it's a spark, just boom. So the piston hardly moves at all during that explosion, if you will. So what happens to the pressure of the trapped gas during the explosion? Right. And it rises a lot. To a first approximation, it instantly jumps to a higher value of the pressure without changing the volume. So in other words, we jump up here somewhere. The ignition of the fuel jumps you almost immediately to a higher pressure for the same volume. So we can think of that as occurring because of heat flow in due to the fuel ignition. So that's what my big fat arrow is. That's heat flowing into the gas due to the fuel ignition. I don't know what that is either. Maybe we're stuck in the lecture demo. I don't know.
Just a minute,
I need to check.
That's a fence, or is that anything?
We're doing something upstairs. Yeah. what they're doing. I'm scared. Yeah. So the fuel burns and raises the pressure, and now the thing's going to expand again. So the trapped gas is going to do work on the piston as it moves down. We're going to get, again, if it's quick, it's practically adiabatic. An engine, it's very high RPM, so very little heat has time to flow through the walls of the cylinder when the piston is moving up and down during any one stroke. So we follow another so-called adiabat out to maximum volume again. But we're always at higher pressure than we were during the compression because the gas is hotter because the fuel was burned. And on the next upstroke, there's exhaust that's let out. So the Q is let out again, basically. And so you can think of it as like, okay, let's then let some heat out during the exhaust. And now the area under the PV curve during compression is different than the area under the PV curve during expansion. So in other words, if I cheat and use the fact that I can draw in different colors, what we get is that the blue area equals work done on gas during compression. That's the blue area. The red area equals work done by gas during expansion. Well, we got a win here because the gas is doing more work on the surroundings during the expansions than is being done on it during the compressions. Why? Because we burn the fuel, is where it's coming from. So net work is done by the gas in the cylinder during each cycle. Which is what we want. We want net work being done so that we can attach this to a car and drive it somewhere. So notice then, just to redraw this here, the net work done is the difference between the red area and the blue area. Right? The red area is how much work that the gas is doing when it's expanding and doing work on the piston and to whatever's attached to the piston. The blue area is the work being done on the gas by the piston and whatever's attached to the piston when it's being compressed. So what represents the net work in every cycle? The area in between the two curves, the expansion curve and the contraction curve. By the way, there's a cute little Wikipedia animation of the two-stroke engine in action there. Boom! Downstroke, exhaust comes out. Boom! Downstroke, oh yeah, I said, yeah, it's actually the exhaust is discharged during the downstroke, is what I meant to say. Not the upstroke. So the idea here is that, an automobile engine and a lawnmower engine, they're both what are called internal combustion engines. Do you know what the internal refers to there? So the work fluid is the gas inside the cylinder. A steam engine is what's called an external combustion engine, whereas gasoline engines and diesel engines are internal combustion engines. What does the internal and external refer to?
Where the gas is located in respect to
Yeah,
the
so yeah, it's if in an internal combustion engine, the combustion happens internal to the work fluid. The work fluid itself is where the combustion is occurring. In a steam engine, the work fluid is steam, but the combustion, you're not burning water. The combustion is external to that. You're using an external flame to produce steam from a reservoir of water. So internal versus external combustion refers to whether it's the gas that's serving as the work fluid inside the cylinder that has the combustion happening inside of it, or if the combustion is happening external to it and the heat is coming in through walls or something like that. So that's the difference. That's what internal and internal combustion refers to, is that it's the fluid doing the actual work on the cylinder, on the piston, that has the combustion happening to it. The combustion is internal to the work fluid. What questions do you have? You look like you have a question.
I'm trying to figure out what would happen if one of the things failed and it just blew up.
It would be terrible. Yeah.
I'm trying to figure out which piece has to fail. Is it the sparking thing or is it the grease?
Well, anything could fail there. Yeah, that valve down there.
Would that like cause it to trail back to the gas line?
I guess if that valve refused to open, you would just stop sucking any fuel in and the thing would very quickly run.
What if it like didn't close?
If it didn't close, then I think let's see. So if it didn't close, if it stayed open,
and like the spark came down and traveled backwards.
I think it would. Yeah, I'd have to think about it. So because the moving is actually so. When it opens is when it lets in fuel.
Mm-hmm.
So if it stayed open,
It would be letting more and more fuel.
I think what would happen is if it stayed open, then during the downstroke you'd be getting fuel, or you'd be getting exhaust flowing there and not just there, and so it would start poisoning itself with its own exhaust is what it comes down to. And then it would quickly.
But would it be enough to like catch the rest of the gas on fire?
I don't know. I'm not sure.
I'm trying to. It should be fail safe, but like if like an engine exploded.
I'm no engineer, so I don't know if it would explode if that valve sticks open, but I suspect it would just stop working pretty quickly is what it comes down to. Yeah. Because you'd be, I think, the richness of the fuel-air mixture would start to diminish because you're keeping exhaust in there, and that would work against the fuel and oxygen being available. You'd be using, and so I think the richness would quickly decline, and as a result, the power would quickly decline, and then it would either really run poorly or just stop running as a result. Something like that would be my guess. So now it's time to stop, but the idea is then that if you can put heat in at the maximum compression, then when it's expanding, it'll do more work on its surroundings than it's done on it when it's being compressed. And the idea with stellar oscillations is if there's a way to get heat to be put into the gas when the star is at its maximum compression, that's what will drive oscillations. And we'll see there is a way for that to happen. If conditions are right, then you can get a situation where the opacity is bigger when the star is smaller, when it's at maximum compression. If the star at maximum compression is more opaque, then radiation energy is getting sort of trapped in it and heating up the gas so that it's like burning fuel heating up the gas. And as a result, the pressure is bigger than it would be if we didn't have this damming up due to the higher opacity. And that means that the thing will expand more on the way out than it contracted on the way down, and it'll start to oscillate more and more and more. So we'll talk about it more next time, but in other words, the interesting thing is that an oscillating star is a heat engine. It actually oscillates because you are adding heat to it when it is at maximum compression. So we'll sort that out.
Hopefully we do that chapter, so we don't have an animation.
What's that?
Hopefully we do that chapter in thermodynamics.
Oh. Well, if you don't, you'll sort of done here.
Woo! We did it.
I just want to be ahead of everyone else.
You what?